let's go ahead and get started. My name is Dan Millison, and I'm the Track 4 chair. And I've been told by the ASEF chair and co-chair that I have to come and introduce the track. So Track 4 is a kind of an experiment in the ASEF program. So we have three main tracks on access to energy, energy efficiency, and renewable energy. Those tend to be a little bit more focused toward, project experience, investment programs, and whatnot. And then Track 4, charting the future of clean energy in Asia, is the idea is that now we have sustainable development goals and we have the Paris Accord, and so our discussion of climate change and clean energy should actually be in this broader framework of sustainable development. So we're not talking about the single tree of climate change, we're talking about the broader forest of sustainability. And so track 4, charting the future of clean energy in Asia, we heard this morning some very interesting remarks from Rachel Kite and from the gentleman with the unpronounceable name about disruptive technology. So we're not trying to do any forecasting here, but rather just have an intelligent discussion that hopefully is kind of a bit elevated above a little bit of what's discussed in the other tracks. We have 6 sessions that are ordered in terms of increasing complexity of the topical content. So we're starting with utilities. The second session in the track is the ASEAN countries' energy transition, then a session on nationally determined contributions, how those might be met, then smart cities, then energy and transport, and the last session, which I will chair, is on the food, energy, water nexus. And so hopefully we're going to learn as we go along, and then in our last session Friday, we're going to be so well educated and informed and have so much knowledge to share that everyone will be amazed. So I'm going to turn it over to my friend and sometime boss, Mr. Rehan Kauser, who's going to take over.
Thank you very much, Mr. Millison, my subordinate at times and my colleague in other times. Thank you, everybody. So we have 5 speakers. One of them is virtual, so he'll be on the video in a while. So let me start off with, I think Dan has given me a good overview. We're here to see the role of the utility in the future. Will they be still relying on the same business models? Will there be transformational changes? Let's find out and hear from them. I think the first one to go is Mr. Mikhail Zibzibadze from Georgian State Electrosystem, who joined the Georgian State Electrosystem in 2007 as head of finance department. He's currently the head of the HR and organization development. He's also worked in telecoms at Telecom Georgia and has degrees in engineering and management. I think Mikhail will be talking to us about on the Georgia case study on how using new technology has helped them resolve the lingering issues of blackouts and other network problems which plague grids all over the world. So with that, I'll pass it over to Mikhail. And Mikhail, 10 minutes.
Thank you, distinguished guests, dear delegates, ladies and gentlemen. It's a great pleasure to be here and to speak on behalf of the Georgian State Electrosystem. My company is in the power transmission business. We transmit electricity from point A to point B, and point A is a location where it is generated by thermal power plants and hydropower plants. Point B is a location where electricity is delivered to the distribution companies and large enterprises and utilities of the country. On the first slide, you see the grid, our network for the year 2010. Our current grid topology is pretty much different. Of course, for the last couple of years, we have built a couple of transmission lines and substations. But this is a snapshot of the situation that we had 6 years ago. list of our customers, as I mentioned, large power distribution companies, utilities, and large enterprises. Next one, please. Let me very briefly explain to you what was the problem of our company. The problem was the following. The largest power plant, hydropower plant, which generates approximately 50% of electricity for the country, is located in the west. And the power distribution and power consumption centers are located in the east, including the capital city. So we have to transmit electricity from west to east, and for that we had a single 500 kV line. When you have that type of topology of the network, it could be regarded as extremely insecure and unreliable. Because of that, when we had an emergency on the 500 kV line, 220 kV lines were unable to handle that much power, and we used to have a blackout in the country or a brownout. Blackout is a situation where there is no electricity supply at all, and we call it brownout a situation when there is no power supply to large regions of the country. And on this slide, you can see the statistics. When you have a situation like that, you can do two things. Number one, you have to start building network infrastructure. That is a great way to tackle this problem, but it's very time consuming. It takes generally 4-5 years to complete a project, and it's very capital intensive at the same time. You have to raise capital, you have to go to the financial markets and raise the capital in the form of long-term debt, which is not an easy thing to do. Or there is another way. You can buy a technology, you can find a low-cost but effective solution to the problem with the help of the technology. So we decided to go the technology way. This is a standard decision-making protocol that we followed. Identified the root cause of the problem, and the root cause was a very weak connection from west to east. We decided to buy a technology. We identified a vendor, very trustworthy, skillful company, US company, SEL. We wrote our terms of reference, handed the terms of reference to the vendor who bought the technology, installed the technology, and it's been working since then. Let me very briefly explain to you how the technology works. It is called the RAS system, Remedial Action Scheme System, or the Emergency Control System, as we call it. So when we have an emergency situation on 500 kV line, when the 500 kV line is open, the system actually cuts out a certain number of customers according to the predetermined protocol and saves the system, keeps the system functional, operational, and alive by matching the generation profile with the consumption profile. So it is an event-based system. When that thing happens, it starts functioning, it starts operating. And since then, the system helped us many times with the help of the RAS system, the help of the ECS technology. Many blackouts and brownouts have been prevented. I have a special slide for that. This is the statistics of how many brownouts and blackouts have been prevented in the year 2014. This is the data for 2015, and this is data for this year. We also tried to calculate the financials of the project for that, we tried to calculate what is an impact of blackouts on the country's economy, and we made a couple of assumptions. Maybe those assumptions are not 100% accurate for calculating the impact of blackouts on the economy, but I think that generally they're pretty much reasonable. So we have calculated how much economy is created in the country per hour, and then multiply that number by the duration of blackouts. For example, last year, in the year 2015, Georgia's economy, GDP, current prices was $14 billion, which means that $1.6 billion worth of economy is created per hour. And when you have a major blackout, it usually lasts at least for an hour. You're losing that much money. And please compare that amount to the cost of the technology, which is just $2 million. And I think that it's pretty much obvious that technology has repaid itself many, many times. And please also pay attention to other consequences of the blackouts. There are some other factors other than money, and this is the PR component of a blackout. When a blackout happens, everybody is unhappy, customers are mad at us, government is upset, and we get a lot of bad press, which is very hard to deal with. So with the technology, no more blackouts anymore. The technology brought some other benefits as well. First of all, it is a learning curve. Technology brought new knowledge to the company. Our engineers are learning how different components of the network are working with each other. The technology itself, the RAS system, is extremely flexible. Yes, we are adding new transmission lines and new substations, and the technology can accommodate these new realities and new topology very easily. With the system, we have created, of course, the communication system, and that communication system can be used for other purposes as well, for transmitting data related with protection systems and power control systems. And overall, the technology helps us and to eliminate the technology itself eliminates the need to procure other expensive devices. For example, it provides us with synchrophasor measurements, and the synchrophasor measurements are very high frequency measurements that help us to control the voltage and the frequency in the network. So probably it's high time to thank you, dear ladies and gentlemen, considering the fact that I'm running out of time. Takeaway based on this case is the following: that there's great technology that is there, it's available, it's cheap, it works perfectly, and the case is sustainable, profitable from the financial point of view as well. Thank you very much.
Okay, thank you very much, Mikhail, on the state of the electricity system in Georgia with the introduction of RAS. Next is Karl Ulrich. He comes to us from CTC Global Corporation, where he's a vice president of strategic programs. And Karl will be telling us, or will be sharing with us, how the choice of conductors is actually helping them reduce GHG emissions. So that's another step that the utilities may be taking in the future. Karl? Thank you.
So I'm going to talk about something that probably no one in the room has really thought about. How does a conductor reduce greenhouse gas? One of the reasons why no one has thought about this is that the transmission portion of our power system is about 5% of the bill to the customer. The power side is about 65%, the distribution side is about 30%, but this middle portion is sort of insignificant and doesn't come into our thinking a lot. But if I said I could reduce the amount of coal that a power plant needs to burn by 2%, reduce the greenhouse gas by 2%, everyone say, yeah, we need to make those changes. So really, I'm just going to talk about in general, very high level, not getting into the details of technology, the impact and the way that conductor choices should come into play when we're looking at a project, whether it's reconductoring existing lines or putting a new line in as part of any power plant. In the US, if we change to efficient conductors, you can reduce the line losses in your system by 1 to 2%. I won't go through the details. I put a lot of details so that you can read and follow up. But this would reduce on the 4 billion megawatts hours in the US of power consumption. This would reduce the greenhouse gas in the system that is generated by 44 million metric tons per year. So this one change, not necessarily a cheap change, but a simple and easy to understand change that isn't being made, can have a big impact on the environment. What makes a conductor more efficient? The basic thing is the more aluminum you have in a conductor, the more efficient it is. And the higher the conductivity of that aluminum, because all aluminum isn't equal, the more efficiency you have. Conductivity and resistivity, which the resistivity creates these line losses, forces you to burn more coal, forces you to create more greenhouse gas in your transmission line, is what we're looking to minimize. But you can't just say, let's go ahead and use more aluminum, because you've got restrictions on your towers and you've got to manage and compare it evenly. So what I'm going to do is suggest that when we're looking at conductors, we have to say, let's make some assumptions about towers. You have to look at the weight of the conductor, the tension you're putting on the towers, your sag clearance requirements. So as long as we keep all of those considerations equal, we're not selecting a technology that can't be implemented on the existing tower systems that are either already installed or are the standards that utilities choose. So if we look at a small line, a 132 kV line in Nigeria that was reconductored, they wanted to add 50% more power to the line. The existing conductor couldn't carry that load. So TCN, the utility in Nigeria, did a comparison of a number of so-called HTLS conductors. They did an analysis not wanting to increase their towers, not wanting to add new right-of-way or rebuild anything. So they used the existing tower structures. So now we can use this as just a general framework. And I'm going to hit fast forward here for a little while and not go into the comparison, but I wanted it in the handout so that you could look at this. Using a software to model the line and the tension load and the sag clearance on the conductor, we're able to look at this increase of 50% power on the existing transmission line and say, what is the tension loads on the towers, what is the sag, and what is the amps that are running through the line? And so that sets the basis of that existing ACSR conductor, the standard conductor that every engineer reaches for first when they're designing a line. So getting this sort of awareness that there's other options on the engineering side is the first step. But looking at that as the basis, we can compare, for example, a bigger ACSR conductor, and you can see that in order to get this power, you can't just put a new ACSR, larger ACSR conductor, the standard conductor, on these towers, because it just weighs far too much and will put too much tension on the existing towers. So when we start looking at HTLS conductors that can add those amps and can meet those tension requirements, we start looking at things like ACSS conductor, popular conductor in the US, similar to TACSR, thermal aluminum conductors used in this region and in Europe. You can see we can add the 600 amps, and we're within the realm of what the towers can handle. So we're starting to make a fair comparison of conductors. All aluminum conductors, another type of very efficient conductor, fits in. You can see we go from adding 150 millimeters of aluminum to having 240 millimeters of aluminum for the AAAC copper. So you're adding much more aluminum. You know it's going to be more efficient. Invar, another very common conductor. You can carry more amps, but you'll notice that it doesn't really have much more aluminum. So it's not going to be an efficient conductor, but it will give you more capacity. And this is an option that a lot of people choose when they're just thinking about capacity. They're not thinking about efficiency. ACCC, you can add more aluminum at lighter weight, and you can have more capacity. So again, you're looking at capacity here, but you're also looking at efficiency because you have more aluminum. So if we get rid of these heavy conductors, you sort of map out what are my conductor options for efficiency. Well, on the project, it basically came down to 4 conductors that they looked at. And you can see that when you adjust the amount of aluminum by the conductivity of that aluminum, that you can add about 40% relative to the ACSR, 40% more conductivity relative to that baseline standard conductor that's installed as the starting point everywhere in the world. What that results in for this small line is about a 30% reduction in line losses. And for the amount of power going through this 10-kilometer line, the savings is only 45 metric tons per year of CO2. It's a small line with a small amount of power. When you look at a bigger line, 120 circuit mile line at ADP in the US, they increased the ampacity. And on this line, 345 kV line, they were able to reduce the greenhouse gas, the CO2 produced per year, by 57,000 metric tons. And again, when we talk about scaling it up in the US to 44 million metric tons, the math is about right on this specific project. 120 circuit mile lines, there's about 160,000 circuit miles of transmission lines in the US. So multiply by 1,000 and 58 million metric tons reduced if you would make this choice of conductor for efficiency. What about the regional impact in Southeast Asia? If you look at the megawatt hours produced every year, the CO2 that's generated every year, and take those same assumptions for efficiency and say a 30% reduction in the greenhouse gas that is lost to transmission inefficiency, that saves 18 million metric tons per year in the region. So it's a big impact. And again, if we said we're going to reduce the amount of coal you burn by 2% at your coal-fired power plant, everyone would say, great, let's do it. But no one's really talking about how do we get the utilities to make this choice? How do we enable them to make this choice and get these benefits? So changing to efficient conductors, you can save up to 2% of the CO2 generation by the same amount and deliver the same amount of energy. For renewables, you'll say, well, if I'm not burning coal, if I've got a wind farm or I've got a solar farm, what do I care? I'm green, it doesn't matter. Well, you're actually delivering 2% more capacity in that case because you're not losing it along the way to resistance. So if you're putting in 1,000 megawatt hydro, you're actually putting in 1,020 megawatt hydro. And there's a 2% better return on your project if you make this choice. And that's the key sort of ending point here. This is efficiency that goes along with better return on capital projects. So the real point is, why aren't utilities making this choice? And we can get into that discussion as we go.
Thank you, Carl, for pointing us in the right direction on the choice of conductors. Next is Yatin Premchand, who comes to us from DNV GL, and he's a principal consultant there. And he's here today to talk to us about drowning in the pool. So there's no pools in ADB, so don't worry, nobody will be drowning here. And bringing on the multi-mart. So I think he's going to be looking at how important it is to capitalize on the emergence of these new market models in Asia. So, Yatin.
Good afternoon, ladies and gentlemen. So I'm going to give a little bit of a background on this paper, or at least this presentation. And the issue right now is that electricity markets around the world are grappling with a situation with increasing renewables penetrating into grids. And that in itself, basically, if you look at the amount of papers and literature that's out there, there's a heck of a lot of it that is criticizing existing markets with their ability to actually deal with this increased renewables. Also, in terms of the complexity of the markets that exist, right? So you've got a whole host of new technologies, new solutions, variability, etc., that's coming into play, and you've got these markets that are built on rules and regulations that aren't necessarily, should we say, compliant to these new or the evolution of energy systems. So with that in mind, we're going to introduce what the concept of the multi-mart, and basically that. To begin with, we could basically share a global survey that we conducted very recently, which basically shows a worrying split between the grid and the renewable energy community. All right, and basically, the grid feels that renewable energy is a problem, whereas in what it should be saying, or what we should be looking at it, is in an opportunity to be able to improve the way grids and markets operate, right? And that's where this disparity is basically coming from. And by improving the way that renewables and intermittent generation and or technologies work with the grid and the markets, we're actually opening up opportunities. Okay? And the key here is to open up opportunities across the board for OEMs, for generators, and unlocking revenue potential. Now, having said that, the next page here. There we go. Yeah, beyond the cost. Part of this problem is due to the fact that the East greatly relies on the West with regards to the systems that have been designed, mature markets, mature quote-unquote solutions, rules, regulations that we've basically adopted and tried to shove in place into the Eastern way of functioning and or grids, needs, and solutions that are being deployed. So with that in mind, we need to start looking at different, more relevant ways that markets, rules, and regulations work for distributed generation, for example, in Asia. We need to start walking away from the ideas of balancing and reliability and start looking more at a variety of electricity types and the needs and uses of these types for developing nations. Okay? Now, with that in mind, basically, we need to start looking again, as I said, in Asia, there's not many markets as such, not many energy markets, and if there are energy markets, they're fairly new. There are some older ones and whatnot. But the key here is to be able to detach ourselves from the Western ways and rules and regulations that the markets have been forged around, and start looking at the ability to develop new regimes, the ability to start the slate from scratch and leapfrog into what we would call, say, the multi-mart, for example. All right, and that basically allows for a less complex, less restrictive market, which enables the different forms of energy to actually take place. One example would be basically to use, or should I say, the replacement of mobile phones with landlines. That was sort of a disruptive technology that took over. Now the landline market has issues, but there's no regulation as such that prevented that from happening. Whereas in some of the other markets globally, there is regulation that is preventing the adoption of renewables and distributed generation. All right? we're already seeing an emergence of new energy markets. They're not necessarily regulated. If you look at these instances of affordability, accessibility, resilientness, and the demand for energy across Asia, you're starting to see, for example, up there in Thailand, people just selling solar systems with storage and a simple sheet basically to connect that. Right? So it's moving away from a conventional market as we know it, where we build a central pool and everybody buys and sells from that pool, and then you've got these central generators and a distribution network. This is looking at off-grid. How do you factor this into that kind of a conventional market pool, right? Likewise, if you look at China and Southeast Asia, across these countries, you've got a large number of basically mobile bikes now, in terms of EVs, electric bikes. Similar to Tesla, these charging stations exist all over the place. But they're not being charged at, for example, in China, it's not money against kilowatt hours, it's time it takes to charge. Right? That's another different way of looking at how energy markets should be working. These things, again, are not connected to any energy or price pool. They're sitting out there, they're being rolled out across economies, whether that's in Thailand, whether it's in Cambodia, in China, in Myanmar. And these are detached from the conventional way we look at energy markets. Okay? So moving now onto the multi-mart itself. Those were just some of the examples how the dynamics of the market is changing. Yeah? The new marketplace, i.e. the multi-mart, embraces innovation whilst allowing all market forms to operate, from complex power pools all the way down to shop fronts. Okay? And that's basically the key here. We should not be looking at the market conventionally as we have. And noting that we are in Asia and that we don't necessarily have conventional markets, we have the opportunity to actually design something that fits the need of these different users as well as the technologies. All right. Now, we feel that the multi-mart is here to stay. It's a concept right now. But having said that, there are, and I'll get into that on my next slide, there are a variety of technologies now that are available basically that enable this mixed use, mixed generation, mixed client type of pool. I mean, you're seeing it in EVs, battery chargers, distributed PV, smart grids, demand response, which you'll hear next in a minute. And all of that basically needs to come together to form a holistic market that addresses the actual needs in the Asian context or developing nation context. So a lot of this would actually relate to Africa, to South America, etc. But in order to do that, what you really need is standards, certifications, and a business to be created out of that, right? To be able to build these pioneering markets. Now we have that capability in DBGL. I have to put in a plug. We have that capability because we have designed and built a majority of the existing legacy markets. And now we're in the position where, for example, if you see that the US EF, that is an initiative that is taking place on a multi-mart sort of framework in Europe, which is addressing the needs of Europe. Likewise, in Asia, we need a similar initiative to get all of our utilities, our regulators together and start developing unique multi-mart type concepts, implementing those for the needs of the specific countries. No country is the same. And then seeing how we can perhaps even link those up at some point to look at a larger marketplace across Asia and the Pacific. And that's where I am. So thank you very much.
Thank you, Yatin, for discussing with us on the multi-mart and how maybe some of these regulatory frameworks or rules and regulations need to be revised to accommodate these changes going forward. Dr. Kamalanath Samarakun, who's a lecturer at the Faculty of Engineering at the University of Peradeniya, is with us, who's actually long worked in the utilities in Sri Lanka, and he's here to speak to us on how demand-side support, consumer behavior, and response can help us absorb more renewable energy into the grids. Thank you.
Good afternoon, all. Now, I've been doing research for last 7 years on how to use smart meters and smart meters data to support the control of the power system, particularly the frequency control and the voltage control. But now, I'm from Sri Lanka, but I have been doing this research in the UK, and it will take some time to get smart meters to Sri Lanka. So I was thinking now whether we can have a simple solution until we get smart meters, or even after getting smart meters, to address some of the problems that we as a nation face right now. So you know, Sri Lanka is a small country or island, just below India, and which is not connected to India. So it's an island country and a small power system. We have about 4,000 megawatt of installed capacity. Out of that, the peak is around 2,000 and the base load is around 1,000. So we have been using hydro, and hydro installation is about 1,500. Now it is exhausted. So because of that, the power system is constrained in many ways. Like if it is a dry year, we don't have power and energy. And on the other hand, since the hydro is exhausted, we get more and more large thermal power plants. So if the base load is say 1,000 megawatts, and if we get 300 megawatts each, and in the same plant 900 megawatts, so you can see how the operation difficulties we face. And since hydropower is exhausted, we get more and more large thermal power plants, and also at the same time we get renewables through net metering, and as well as there are many hydros installed, and it is almost exhausted again. So these things, as you know, we face operational problems because they are large, and to maintain N-1 reliability, we have to have large spinning reserve. So usually we don't maintain about 300 megawatt spinning reserve. It may be about 100 megawatt. And then the one reason is it is very costly to maintain, and also we don't have sufficient energy, so we can't keep the spinning. Mainly the frequency control is being done by the hydro. And if those thermal power plants are private sector, so they would like to run at the maximum, and some of the power plants we can't run at partial loads. So in an event of a generation loss, the frequency drops very quickly, and that cause to trip other thermal power plants because they are sensitive to frequency, and most probably leads to blackouts. And solar power plants, we are getting more and more power plants, rooftop solar panels, but they are not supporting, we can't dispatch, and they are not supporting frequency control. And the last resort that we have is the load shedding, under frequency load shedding, to maintain the power system. And economic loss due to unplanned outages, unplanned interruption is very high, and it's about 0.3% of the GDP, around 280 billion US dollar. So load shedding, the worst part is the load shedding cut off the renewables when it is needed, because they are connected to the distribution system. So what I'm proposing is, it's not a rocket science, and it's a simple thing, but I'm proposing it to introduce at this moment to the building permission, building planning permission, that is to have 2 bus bars in household level, and in the domestic level, and also in the consumer level. And one is essential for lighting and sockets, and the other one is non-essential lighting and sockets. And we can have a simple controller which detects the frequency and switch off the non-essential when there's a frequency drop. And we can do it at a higher, just below the operating frequency, rather than waiting to drop the frequency to a very low level. And then demand response is not a new thing. In the UK, they are using this frequency control demand management, FCDM, national grid, to get demand response from the large consumers, And even in the USA, they have aggregators like Inanoc, which gives the demand response. And at the bottom level, appliance level, the dynamic demand of the UK, they are fixing electronic component to detect the frequency and to switch off the appliance. And also in USA, they have proposed grid-friendly component. It's again an electronic device. So I just calculated some of the financial implications, but these are just some crude assumptions. So by spending maybe about half of the economic loss of Sri Lankan power system, we can do the modification to, this is very, very rude approximation, for 5.4 million consumers, ignoring the benefits like cost of spinning reserve, the saving of the spinning reserve, and also economic benefits, and the customer comfortability. Ignoring all these, it is possible to do it in financially reasonable way, and if we can plan for the new houses, if we can introduce this, it will be very beneficial. So I have done a simple testing. So this is a single bus bar model, and this particular scenario is taken from its reference, where when the total load is around 1000 megawatts, 165 megawatts is combined cycle gas turbine was tripped, and load shedding stage 1 was operated, 2 was operated, and when the governors are start to respond because of the low frequency, GTU, another gas turbine trips due to under frequency. So then the load shedding stage 3 also started, and then only the system started working. So we passed 3 stages of under frequency load shedding. But if you can have between 25 to 100 megawatt demand response, from the simulation we can see the gas turbine plant did not trip at all, and in the case of 25 megawatt, only the stage 1 was operated, but in the case of 50 to 100 megawatts, none of the load shedding was operated. So by looking at it, I think it is feasible, and so to conclude, I think so it is desirable to have demand response, and if we can start now for the new buildings at least, eventually we'll be having this non-essential and essential bus bars in the system, in the households and the installations. What I think is that now the utilities, we are trying to give 99.99% of the time to supply give the supply to the consumer. But when the utility is in trouble, I think it is a responsibility of the consumer to support the utility. So this is what I feel. And of course, the utility should and can compensate the consumer for providing the demand response. But this is a simple device that I am proposing, but I've been testing different algorithms, and because now the controllers are not that expensive. So you can have controllers, and you can have any complicated algorithm inside the controller. But this is just to cut off the non-essential bus bar. And so I think yesterday Professor Distop mentioned that the same word, paradigm shift, the demand response will be a paradigm shift, and I have included that before the hand this same word. So I think it will be a paradigm shift, and I think we have to start thinking about demand response without disturbing the system going down, cutting off all the lines, just cut off only the non-essential. Thank you.
Thank you, Dr. Samarakun. So it's not, I think we have to switch to demand-side response. So the last speaker, who's with us spiritually but not physically, Mr. Alex Zapantes. He comes to us from the Institute of Carbon Capture and Storage, where he's the general manager in Australia. Prior to this, he was with Rio Tinto, and I think Alex is now online, as you can see him up there. So Alex, welcome to this event, and your presentation is up and ready to go, so 10 minutes to convince us that CCS is the way to go.
Okay, thank you. Hopefully you can hear me. If you can't, please yell now. So it's a great pleasure to be not with you today, but to be with you in spirit here from Melbourne, Australia. So CCS, quite a controversial topic it seems in the energy and climate debate because of the perceived lack of progress around CCS. So I'll share with you today 10 or 11 slides where hopefully I will convince you that CCS is actually an essential part of any portfolio of technologies and strategies in order to achieve climate goals. So let's jump straight to the answer as the first slide. This is the outcome of International Energy Agency modelling that many of you will probably be familiar with, and what it does is it shows the contributions of various technologies towards achieving emissions reductions consistent with a 450 ppm stabilisation case or a 2 degrees Celsius or 50% chance of a 2 degrees Celsius temperature rise. And you can see that CCS, according to the modelling, is required to contribute 13% of all of the emissions abatement in order to achieve that goal. About half of what renewables are required to provide, about 30% of emissions reduction from renewables, and end-use energy efficiency, where the greatest opportunity is, nearly 40% of emissions reduction provided by end-use energy efficiency. Of course, this is for a 2-degree world. The recent meeting, COP21 in Paris, set us on hopefully an even more ambitious track of attempting to achieve a 1.5 degree increase rather than a 2 degree. Under that scenario, and we haven't yet seen the latest reports by the IPCC into what that means, one would expect that the importance of CCS just increased. In fact, just as the importance of every technology just increased. The other thing to remember, of course, around all this modelling is that it is a computer general equilibrium model, and therefore it seeks to find the lowest cost solution. So any deviation from this portfolio of technologies actually results in an increase in cost in order to achieve the same climate outcome. On to the second slide now. The purpose of this slide is to answer the question, well, renewables are growing very rapidly, spectacularly, doing extremely well. Why can't we just move away from fossil fuels completely and go to a 100% renewable future? Well, the modelling shows that is in fact not feasible. In fact, the IEA modelling shows that compared to 1990, the share of fossil fuels in the global energy mix is about the same. In fact, it's about 81%. And in 2040, they're projecting a fossil fuel share of about 75% of global primary energy demand. The other thing you need to note, though, is that although the relative share of fossil fuels in the global energy system has reduced, the absolute amount has increased. And that's because, of course, energy demand continues to increase, even considering the expected improvements in efficiency that are coming down the pipe due to various technological improvements. So the bottom line is that in 2040, there's going to be more oil, gas, coal, fossil fuels utilised, burnt than there is in 2013. And somehow we need to deal with those increased emissions that are going to arise from those fossil fuels. The next slide shows some modelling that the IPCC did, published a couple of years ago. And what the IPCC did was really quite instructive and interesting in that there are a few scenarios where they assumed various technologies were not available to play their full role in achieving emissions reductions. You can see the smallest bar on the left there, nuclear phase out. If nuclear is completely phased out, you would expect the cost of achieving the same climate outcome to increase by about 7%. The next stack bar to the right, if deployment of solar and wind renewable energy technologies was limited, you would expect that to increase the cost of achieving the same outcome by about 6%. If bioenergy was limited, you'd expect that to increase the cost of achieving the desired climate outcome by about half, by more than half actually, by 64%. And if CCS was not available as a technology option, you would expect the cost of achieving a 2-degree outcome to more than double, to increase by about 138%. And that makes perfect sense when you understand how, from the previous slide, the demand for fossil fuels is increasing and is projected to continue to increase, albeit at a slower rate than has been the case, especially over the last decade, when the rate of increase has been unprecedented due to the emergence of China mostly, but still increase nonetheless. Of course, the other point I'd like to make at this stage also is that we need to consider fossil fuel emissions not just in the context of energy and transport, electricity and transport. We need to consider the use of fossil fuels in the context of providing feedstocks to various industrial processes, steel production, coal to chemicals, fertiliser and the like. Approximately 25% of global emissions today come from the use of fossil fuels in industrial processes such as steel production, where there is no feasible alternative. You cannot substitute those other materials for those fossil fuels in those processes, and the only technology that is available today that can deal with those emissions is carbon capture and storage. On to the next slide. What this slide shows is that currently there are 40 large-scale CCS projects with a combined capacity of 71 million tonnes per annum of CO2, that is to capture and store. Now that sounds somewhat impressive, I guess, 40 large-scale projects and 71 million tonnes per annum, but compared to what is required, it's very small. As you can see, the dot here on the left represents how much is currently in place today, and the square made up of many dots on the right indicates what is required in order for CO2 to play its full role in emissions abatement. So the question here, the critical question here, is can CCS be scaled up at the rate required to play a significant role in emissions abatement? So a key learning, I guess, from our experience globally with the magnificent success of renewables is that strong policy drives investment. The bar chart, which you can see there, shows the relative investments of all clean energy on the right, the toolbar, versus carbon capture and storage. And you can see that the investment in all clean energy is many times higher. It's about $1,929 billion US dollars over the last decade or so. In comparison, the investment in CCS is of the order of 20 billion. That's a very round number. It's probably a bit less than that. And there's a reason for that. And the reason for that is that CCS simply has not enjoyed the same sort of support that renewables, for example, have enjoyed, and therefore the business case for investing in CCS simply hasn't been there. Enhanced oil recovery has played a very important role in the progress that CCS has made to date, because what it does is it provides a revenue stream for your CO2 rather than your CO2 disposal being a cost. That alters the economics of the projects very significantly and allows those projects then to proceed. So the question is, how do we get CCS onto a similar curve as renewables? Next slide is quite instructive, I think, in terms of putting some numbers around why renewables have done so well. So as I said, renewables, fantastic success story, fantastic rates of deployment. They need to continue to deploy these sorts of rates, and in fact, the rate of deployment needs to increase in order to achieve 2 degrees. But we need to remember that CCS also needs to be deployed at a very fast rate, and deployment needs to increase very significantly from rates that we've seen historically. We only have one commercial scale coal-fired power plant with CCS, for example, operating at the moment, and that's the one operated by SAS Power in Canada. So I'm originally trained as a physicist, so I love numbers. And if you look at this chart, which is from the World Energy Outlook published by the IEA a couple of years ago, and you integrate, as I've very roughly done in this chart, under the curve between 2007 and 2016, you can see that very roughly the value of the policy support that renewables have enjoyed in that period is around about $800 billion US dollars. Now, if you do a similar exercise for carbon capture and storage technology for deployment, you'll find that the total policy support for CCS over all time is of the order of 20 billion. In fact, it's significantly less than 20 billion. I'm being conservative by saying it's 20 billion. So So we really do need to have much stronger policy support for carbon capture and storage if it is to undertake its full role in mitigating climate change. We need policy parity is what the Institute likes to call for, so that the same sort of support that renewables have enjoyed and should continue to enjoy is also offered to carbon capture and storage. What about the other benefits of CCS? I know I'm running short on time, so I'll be very quick here. CCS delivers emissions reduction, that's its primary benefit. Of course, if you put CCS on a plant, you'll also achieve very significant reductions in NOx and SOx and particulates, but frankly, you can achieve those reductions without CCS, you can achieve those reductions just with standard pollution control equipment on your power plant. The other sorts of benefits that CCS do provide, though, will depend on a particular plant. So, for example, using SAS Power boundary dam as an example, one of the significant advantages that SAS Power saw in going down the CCS route is it effectively completely removed any fuel cost risk for them. They knew exactly how much their coal was going to cost them effectively forever. So a significant economic advantage to SAS Power. And the other more general benefit of carbon capture and storage, in addition to, of course, its emissions reduction, is the fact that it's thermal power, dispatchable baseload power, and provides all the grid services that any other dispatchable baseload synchronous generation with inertia provides. So all of those issues around trying to manage the grid, a thermal plant, gas or coal with carbon capture and storage helps to ameliorate those issues because it provides those services which we currently take for granted. And that will become ever more important and more valuable as the penetration of renewable technologies increases in grids in order to reduce emissions. In terms of rates of learning, these are some figures that have been provided by the US Department of Energy, and they're fairly consistent with what we're hearing from SAS, for example. A 20% reduction for the second generation technology, a 20-30+% reduction in sort of nth generation technologies. Exactly what that looks like, we don't know. We don't have a crystal ball. It is clear, though, from experience in pretty much every other large industrial process that with deployment, costs come down. In terms of providing modern energy services, a lot of the discussion around the provision of energy to people who currently don't have access to energy has a quite a low level of ambition. The IEA talks about 250 kilowatt hours per year from memory being energy access. If you want to supply people, communities, economies with modern energy services, you require something of the order of 7,000 kilowatt hours per capita per year, which is the average for Europe, very roughly. So this drives economies that are developing in Asia, Africa, and elsewhere to look for low-cost, large generators of electricity, such as coal and gas. And this is why, according to the Climate Tracker, there are nearly 2,400, I think that should be, new coal generation plants to be built by 2030. They are relatively low cost, they are relatively low risk in terms of operation and reliability. They provide large amounts of electricity which is required to develop their economies, and they do it at relatively low cost. And they use domestic or readily accessible resources, gas or coal resources. So the true value of CCS is that it allows the continued use of those resources to support sustainable development, whilst also achieving climate goals. That really is the true value of CCS. Enhanced oil recovery, as I mentioned earlier, is extremely important in the early deployment phase of CCS because it enables larger projects to proceed where there isn't sufficient policy support. EOR provides a revenue stream for your CO2, which makes these projects possible. EOR is not the answer to climate change, but let me be very clear on that. EOR is a good thing. We need to be supporting EOR projects as much as possible because the CO2 that is injected into the ground in order to extract the oil does end up sequestered, permanently sequestered. Some of it goes around several times, it is collected and re-injected, but once the production is finished, the CO2 remains sequestered in the ground in the same structures from which the oil and gas have been extracted. There's a question in some people's mind around whether the emissions from the use of the oil that is produced as a result of the EOR are greater than the emissions saved by the sequestration of the CO2. The simple answer to that is that that's quite a simplistic assessment. The reality is that if the oil wasn't produced from these particular fields using EOR, another field somewhere else will simply ramp up the production very slightly and produce that oil. So there's no impact on oil demand. But EOR is not the answer to climate change. It's very important to early stage CCS deployment. Going forwards, there's going to need to be a lot of CO2 sequestered in saline aquifers. That's a whole other presentation. So I'll stop there. Sorry, I've gone slightly over time. Thank you for your attention, and I'll leave it there. Thank you, sir.
Thank you, Alex. You must have read my mind. I was about to tell you to please bring it to a close. Thank you very much. Yeah, thank you. So we had 5 presentations. I hope they were useful and interesting. But I think basically the message is that the future of the utilities is all moving towards low carbon, and of course with a greater presence of renewables. And of course, will we still rely on the business as usual model, or will these utilities be looking for new utility streams or new ways to do business? Maybe against the existing regulatory frameworks, it may not be possible. So there'll be a need for a paradigm shift, as someone said, a change of thinking. So with that, let me just, having said those concluding remarks, open up the floor. And if there's anybody brave enough to ask a question, then please stand up and direct them towards 4 + 1 on the screen. 5, they're all yours for the next 20 minutes. Let me open up with a question which was suggested to by my friend Dan this morning. He said after the end of this presentation, ask the audience, would anybody actually put their money in any of these ideas that they put forward today? So with that, let me start off. Dan? Carl?
I'd like to know. I'll get started.
Okay, so is there anybody from the utilities looking to purchase conductors? Please contact Carl for further information. Special discount given at they said. So it's all clear? Yeah. Okay. So yes, please. The first one gets a gold set. No, that's a joke.
My name is Telaka from Sri Lanka. I have no questions to the presenters. Maybe I can pose both of them together.
Sure.
Right. Mr. Ulrich, we had this deep dive workshop last time. And what we generally gathered is that the HTLS conductor is about double the cost of the standard equivalent conductor. So, except for locations where you have constraints on sag and other mechanical parameters, the energy saving as well as the environmental benefits are actually incremental to justify the use of a HTLS conductor. Now, for the utility of the future to have only HTLS and nothing else, what should be happening? I believe the costs should come down so that the conventional conductor should go away even for a new greenfield line. That's the first question. Second question is to you about Sri Lanka. The device you are proposing, will it, when the frequency recovers, will it pick up the dropped load of the customer? Thank you.
Carl, please.
Yeah, it's a good point. The conductor pricing is going to be 2 to 3 times the price of an ACSR conductor. And it will go down with larger usage on bigger projects, but you know, as you saw, you're adding 30, 40%, 30% more aluminum, so you're going to obviously be 30% higher than the standard size weight of the ACSR conductor. But it is an incremental benefit that pays off in usually around 5 years or less. It's probably adds for a new transmission line, it adds about 10 to 30% to the project cost, total ticket price. And so then that's recovered over 3 to 7 years usually. That's without considering any benefit for carbon credits or any sort of impact that making that environmental choice might make. That's strictly just on what could be realized with the additional either savings or power sold.
Here's the application or the device that I propose that will reconnect the device or the non-essential bus when the frequencies will be covered up to over 50 hertz, like that's what we do in the load shedding. But just another paper I wrote now, there we can have different time scales for different appliances. We want to have an advanced algorithm for how many you can adopt for a couple of seconds. So depending on the algorithm that you're proposing, you can have different payback or recovery schemes. But this one is just for 50 hertz.
Yes.
Hi, I am from the University of San Diego in California, and I have a question for, I work in the academic world, so I have a question for Mr. DNGL, DNVGL.
Mr. Yati.
Okay, sorry. First question is, what are the type of batteries that you see are being sold in these smaller Asian markets, which is interesting. And the second question is, you mentioned there's a need for standards and certifications to be developed. Who is developing such standards already, or who do you think should be doing so?
That's interesting. In terms of batteries, lead acid would be the common type of battery, at least for the smaller scale. But then if you start looking at 100, 200, 400, 500, and up to megawatt scale, then things change. The dynamics actually change based on the use and the utilization needs of those batteries. And I can go on most probably the entire day on this, just because I had a whole day of meetings yesterday on exactly this subject with some utilities here. So we can maybe take that offline. One of my colleagues is here as well, who you can speak to about that. With regards to the standards, DNVGL is actually involved in standards development. We've been doing it for 150 years now as a certification and accreditation body. And with our experience for about 90 years in the energy business in Europe and North America, we've been involved in quite a number of standards development initiatives in other areas of energy. So with the market designs that we put in place over the past few decades and the new ones that are coming up that we're involved in, we can actually be able to identify with the market participants and the regulators how to craft those standards that could be replicable across similar environments.
My name is Satya Kumar from Sri Shakti Alternative Energy. My question is to anyone in the panel. Traditionally, utilities have been organized with a hierarchical structure of generation, transmission, distribution. Now, when you're talking about disruptive technologies, and we have seen it happen in the IT industry, from mainframe, come to PCs, tablets, and smartphones. It's completely, computing power is distributed. Now, when we're talking about distributed power, do you see this kind of disruption affecting the traditional utilities? If so, how will the utilities be shaped in future? I think, if you have read the book Third Industrial Revolution by Jeremy Rifkin, he talks about this kind of disruption. So I want the panel to comment on that.
Okay, so who's going to be brave enough on the panel Nikhil, you looked at me twice, so why don't you take it?
Okay, thank you. Yes. I can say for TSOs, transmission system operators, for what we see in our country, yes, we have introduced for the last couple of years a lot of disruptive technologies. For example, we have completely replaced analog protection and control systems with digital ones. Right now, all our substations at 220 level and higher are equipped with digital control and protection systems, and also the technology that I was talking about could be considered as disruptive. So yes, we see more and more smart devices in the grid, and definitely this is the future. I personally see less disruptive technologies in power distribution level.
We hear a lot about these distributed power generation, small scale solar storage in remote areas of Africa, for example, and that is sort of akin to what the questioner had asked about how are we going to change, or is there going to be this disruptive change with a lot of these distributed generation. And I was at a conference recently, and the thought just struck me is that they're creating a demand for power where there is no supply of power currently. And once they create a large enough market, I think, at least my parochial mind just assumes that the transmission, the grid operator is going to run a line in there and start providing that power and taking advantage of that market creation. So it doesn't deconstruct the whole system. I think that just the efficiency of the system we've put in place will probably mean that the structure, to my way of thinking, will remain relatively similar.
I'd agree.
Mr. Kauser, can I comment?
Yeah. We're overseas.
Hi, thank you. Sorry, it's Alex Apantis here from GTCSI. I think what we're already seeing here in Australia in developed country systems is a disruption of the market. For example, here in Australia, also in Germany, where there's quite large renewables penetration, what we're seeing is a reduction in the wholesale price of electricity as a consequence of renewables being able to bid into the market at very low prices, or in fact effectively zero prices. A reduction in demand for peak generation for thermal power, which is reducing the revenue streams of the generators, which is having a very dramatic effect on the financial liability of the conventional thermal generators. This is causing things such as capacity payments to be considered by governments. In other words, paying generators just to keep their plant operating that would otherwise not be commercially viable, and they would otherwise close it down. Another sort of policy measure which is being considered to deal with this is, rather than charging people per kilowatt hour of usage, there is talk about charging consumers for access to the grid. So the grid services that are provided by a normal synchronous generating plant that we take for granted are not provided by renewable generation, and no one has been paying for those services. So there is consideration, active policy consideration around requiring consumers to pay a much larger fee just for connecting to the grid to cover those services, and of course to continue to pay per kilowatt hour. So we're already seeing a significant disruption in the markets, electricity markets, here, certainly in Australia, and certainly in parts of Europe as well, particularly Germany.
Okay, thank you, Alex. Next, there was somebody there. There.
Hi, my name is Harsh. I work for Customized Energy Solution. I have a couple of questions. So one is for Edwin. Just wanted to know, I've been seeing a lot of off-grid systems and rooftop systems coming up, and they're all using excellent inverters, solar panels, batteries. They're all certified and they have a standard. But overall, the system kind of fails, and the efficiency is even less than 50%. So, are you working on that front? And my second question is to Carl. It's an amazing study which you showed. So, is there something similar for underground cables? And which conductor is the best? Thank you.
Thanks for that. Yes, we are. We are working on not only standards, but we are investing quite heavily on tools and solutions that enable modeling of connectivity between different types of equipment. The performance of that movement with respect to the end use. And we've actually got projects running, not just, in Asia we've got projects running on both the off-grid, the microgrid, all the way up to even utilizing storage solutions for curtailment and savings from using storage. So yeah, there are standards that are being developed globally for systems on a systems level, and those standards and those design mechanisms basically will improve the reliability and the ability for engineers to be able to replicate more reliable systems, as you say, more efficient systems that don't fail. But we're seeing a lot of these failures because just taking a battery in a solar system and a diesel generator and putting it together, and you're like, yeah, it should work, but it doesn't. There's a lot of other more hardcore sort of engineering modeling that needs to go in to be able to connect it appropriately for it to work efficiently for a long period of time and give you those savings.
Yeah, I haven't seen anything on the underground cable portion, but I think that the mindset is the same there, is that it's about designing to the capacity that you plan on going through it, not anything about efficiency. If they do oversize a system, in effect, the only reason they would add more capacity than what the current project calls for is if there's some planned expansion or some optionality that's built into it. So I haven't really seen anything on the underground side.
Yes, please. Yeah.
Hello, this is Bess from DMEGM, same as Yatin, so we can follow up on energy storage later. I have a question for Alex, as well as a comment to the question raised earlier about distributed generation of distributed utilities regarding Jeremy Rifkin's book. I guess first question to Alex. I'm wondering, have we evolved from the talking about CCS to more discussion about CCUS? Because you mentioned, right, if there's no value that you can actually put into the carbon dioxide, I don't think there's a long-way pathway to actually just put a price on CO2. I mean, we have to start thinking about putting waste as, thinking of waste as resource. I was sitting through waste to energy session yesterday also, and I think the whole mindset should be more about, you don't just think about managing something that's, you have to deal with it as a problem, but it's also like, you want to manage it because it's a valuable resource. You want to extract what you can get out from it. And I think the discussion about CO2 should be towards the same, same line. And I'm wondering whether your institute or communities or people that you work with have, actively engaged, because to my knowledge, there are different kind of technologies available for carbon dioxide utilization for different end use. So I guess I'll leave Alex to comment first, and then I'll provide a comment.
Thank you, and that's an excellent question. I absolutely agree. If we could find a use for CO2 which has commercial value and which could create a demand which is sufficient to deal with the amount of CO2 that's being produced from the use of fossil fuels today, that would be fantastic. And there is quite a lot of work going on around the world to try and identify uses for CO2. The difficulty with finding a use for CO2 is its chemistry. I'm not a chemist, so I'll probably get this wrong. If there are chemists in the room, they're going to squirm and go cross-eyed, no doubt. But CO2 sits at the bottom of an energy well. In other words, you need to put energy into it in order to transform it into something else. So its chemistry means it's not well placed for being something which is of value due to its chemical properties. which makes finding a valuable use for it much more difficult. So hence really the current uses for CO2, which actually result in the CO2 being sequestered rather than just being cycled through another process and being emitted at the end of another process, are really quite limited, and at large scale really are limited only to enhance soil recovery. And the real challenge here is the massive CO2 that we're talking about. So a single power station will emit around 1 million tonnes of CO2 per year, and there are thousands of power stations around the world emitting around 1 million tonnes of CO2 into the atmosphere per year. So no one's managed to crack it yet to identify a commercial process to transform CO2 into a product that has value and also has a market which is significant in relation to the amount of CO2 that we need to sequester. But if anyone has any brilliant ideas, I certainly would love to hear them, because that would make the challenge so much easier.
You just remind me to go back and talk to Bartos over coffee, one of those innovations that we should be investing in. Coming to the earlier question about distributed utility future, I actually was in Beijing in April when Jeremy Rifkin actually went in to give a presentation. Actually, for those who are not or following a lot of the utilities discussion or energy discussion in China, so the 13th five-year plan, actually, I think they're trying to be doing something quite experimental. As you all know, like the Chinese utility is mostly dominated by two big state grid utilities. But then in the next 5 years, they are actually trying to push for the kind of distributed opening up in the retail sectors for new communities, for new distributed utility, community level utility grids. Okay, and forcing the state grid to open that space up for new business models to come in, because the government sees value, not maybe in the efficiency point from the physical grid infrastructure, but from an overall economic point, from an economic value creation, new businesses, new companies, new technologies that would enable, and they are pushing for that. While on the other side, they are also making more space for the state grids by pushing them towards the super grid, meaning connecting China and Japan and Korea. And so still, there's this dilemma that they are making the state grids to be stronger, bigger in the transmission side, but then to lower down in the distribution side, they see that as inevitable. And then they're trying to play about it from the other side, meaning opening it up so that there are actually more players and more companies and more products and more businesses. And I think that's that's something that I think for those interested, we can follow on this experiment that the Chinese are doing. Thanks.
Okay, thank you. We have 2 minutes left. Anybody? Okay. You can have the last 2 minutes, yes.
Hi, my name is Jitine Ho from ELO Solutions. I just want to make a comment on Beth's question on the use of CO2. There's two things you can use CO2 pretty readily. One is in greenhouses, the other one is in carbonated drinks. Actually, there are quite a few talks about how do you move CO2 into greenhouses so that you can use them to produce more food. Just some ideas to share, that's all I have.
Dan, I think you wanted to say something, so.
Dan Millicent again. Alex, we heard some this morning about some new proprietary technology for doing a bio coal, basically a biomass concentrated to comparable energy density as coal, and that there's a prospect for pretty rapid growth of that process technology where conventional coal could be replaced with biocoal. There we would get this. We'd be addressing the full coal supply chain, getting that broader forest of sustainability that I mentioned earlier. There is another use for CO2, and the chemistry reaction is calcium oxide plus CO2 yields calcium carbonate, also known as limestone. That reaction is exothermic, and there is some commercial R&D going on to try to perfect that so that you can actually get cement or limestone as a byproduct of CO2 capture. And when you make limestone out of CO2, you're going to have that stored. That's a very stable a mineral form. It's effectively going to be the same as if you put CO2 into a brine aquifer with in a limestone aquifer. Also, if we just picking up on what we heard this morning from some of our keynote speakers, if we want to look at, again, the broader forest of sustainability and look at ecosystem protection, look at marine resources, look at forest resources, we should be investing more money into sequestering carbon in forests and coral reefs, where we're going to actually get much, I think much greater public health and ecosystem services benefits. Again, the policy making exercise on this hasn't really been very robust, and there hasn't really been much in terms of, market breakthrough to lead that transformation.
Okay, thank you, Dan. I think on that, the session has drawn to a close with respect to keeping it on schedule for the next set of speakers and next people to come in. So let's give one large applause to 4 plus 1.
Thank you.